Suppose we have some polar curve, r equals some function of theta. I don't actually like to call this f. I like to write r equals r of theta, showing that r has a functional dependence on theta. So if I write r equals r of theta, the slope of the tangent line is still dy dx. How do we calculate the slope of the tangent line? Well, we have to keep in mind the following formulas. X is r of theta cosine theta, and y is r of theta sine theta. If that's true, note that dy d theta is dy dx dx d theta by the chain rule. It follows then that dy dx is dy d theta divided by dx d theta. It follows then that dy dx is r prime of theta sine theta plus r of theta times cosine theta, applying the product rule, divided by r prime of theta cosine theta minus r of theta sine theta. Where are the horizontal tangent lines? They'll occur when the numerator is 0 but the denominator is not. Where do we get vertical tangent lines? They'll occur when dx d theta is 0 and dy d theta is not. Notice that if both dy d theta and dx d theta are 0, that gives no real idea of what's going on. We know that in the context of limits, 0 over 0 just means more work. Let's look at r equals 1 plus sine theta, and let's find where the vertical and horizontal tangent lines are. For the vertical tangent lines, we require dr d theta equals 0. Remember, that's r prime of theta times sine theta plus r of theta times cosine theta. In this case, r prime is cosine. So we'll have cosine theta sine theta plus r of theta, which is 1 plus sine theta times cosine theta. As you can see, when we distribute, we'll have a cosine theta plus cosine theta sine theta plus another cosine theta sine theta. That's 2 cosine theta sine theta. To solve this equation, it's best if you factor. Please don't use the double angle identity for sine here. Not everything that is possible to do is advantageous. So in this case, we'll factor a cosine theta out and have another factor, 1 plus 2 sine theta. The zero product theorem, which says that if you have two things multiplied together that give you 0, then either the first factor is 0 or the second factor is 0, implies then that cosine theta is 0 or sine theta is negative 1/2. So where is cosine equal to 0? 2 and 3 pi over 2, of course. Sine is negative in quadrants 3 and 4. So we're looking for a place where sine theta is negative 1/2. The reference angle will be pi over 6. That gives us 7 pi over 6 and 11 pi over 6. Let's see if this corresponds to what we would believe given this graph. This is a cardioid. In the theta r graph, we have a vertical translation of 1 and an amplitude of 1. We have a sine curve which always starts on the midline, completes one cycle in 2 pi units, crosses the midline at pi, reaches a max at pi over 2 and a min at 3 pi over 2. The graph then starts with a radius of 1. At pi over 2 we have a radius of 2. By the time we reach pi, we're back to a radius of 1. At 3 pi over 2 we get a radius of 0, and then back out to a radius of 1 at 2 pi. Where are the horizontal tangent lines? Well, certainly we have something going on here at pi over 2. 3 pi over 2 looks like it might be a place where r is equal to 0. We might have dx d theta equal to 0 there as well. We could have a problem. We're going to have to check this one. 7 pi over 6 puts us here, and 11 pi over 6 puts us here. So we need to check this root for the derivative dy d theta at 3 pi over 2. Let's calculate dx d theta, which we know to be r prime of theta cosine theta minus r of theta sine theta. Remember, r prime is cosine, so we'll have cosine squared theta minus r, which is 1 plus sine, times sine. Cosine squared minus sine squared is cosine 2 theta, and we'll have minus another sine theta. 2 times 3 pi over 2 is 3 pi. Cosine of 3 pi is the same thing as cosine of pi, which is negative 1. So we're subtracting the sine of 3 pi over 2, which is negative 1, and that's 0. So we know that there's no conclusion about this particular point. In fact, we can see from the graph that it doesn't have a tangent line there at all. That's a cusp. Continuing our analysis to try to find locations of where we have vertical tangent lines, we'll back up to this spot, and we'll have dx d theta. We'll have cosine squared minus sine squared. Cosine squared is 1 minus sine squared. We'll have a minus sine and a minus sine squared. This simplifies to 1 minus sine minus 2 sine squared. Multiplying through by negative 1, we have 0 equals 2 sine squared plus sine minus 1. Let's see, we need a plus and a minus. So we get sine theta equals negative 1, or sine theta is 1/2. Theta equals negative 1 is at 3 pi over 2, and we already know that we don't have a vertical asymptote there. That's a cusp. Alternatively, we are looking for places with a reference angle of pi over 6 in quadrants 1 and 2, because sine is positive in those quadrants. We'll have pi over 6 and 5 pi over 6. That'll be these locations where we get vertical vertical tangent lines. We're next going to discuss area in polar coordinates. Suppose we have some curve given as some function of theta, and we would like to know the area of some sector. What we'll do is we'll divide the sector into little pieces of width d theta. Each of these are going to be approximated by little sectors of circles. The smaller we make d theta, the more accurate this representation. Do you remember the formula for the area of the sector of a circle? If you have a circle and you're trying to find the area of some sector with an angle theta swept out in radians, how do you find the area? The area divided by the area all the way around is equal to the angle theta divided by the angle all the way around. As you can see, pi is going to cancel. We'll multiply the r squared over, and the area is 1/2 theta r squared. The little element of area that we get, infinitesimal bit of area that we get in this little sector, is then 1/2 times d theta times the radius squared, where the radius is given by this function of theta. To get the entire area of this region, we add these up from theta initial to theta final, 1/2 r squared d theta. This is a formula you need to memorize. For example, suppose I have the cardioid 1 minus sine theta, and I want to find the area inside of this entire cardioid. The area will be the integral from 0 to 2 pi of 1/2 r squared d theta. We'll have to FOIL this out first. We'll have 1 minus 2 sine theta plus sine squared theta all times d theta. Before doing any more simplification, you should note something. We're integrating this sine function in the middle from 0 to 2 pi. If you integrate a sine function from 0 to 2 pi, you will get 0. We'll cross this term out right now. It contributes nothing to our answer. The next step requires that we use a half-angle identity. You integrate sine squared or cosine squared using half-angle identities. So this will be 1/2 the integral from 0 to 2 pi of 1 plus 1/2 1 minus cosine of 2 theta d theta. You need to remember that half-angle identity. What is the period of this function? The period of this function is pi. We're integrating over 2 full periods. If you integrate cosine over 1 period, you get nothing. If you integrate cosine over 2 periods, you get doubly nothing. So this is 0. All that's left is 1 plus 1/2, which is 3/2, times 1/2. We'll have 3/4. When you integrate a constant between a and b, you get the area of a rectangle. The area is going to be k times the length of the interval b minus a. In this case, we get 3/4 times 2 pi. Cancel first. The area inside of this cardioid is 3 pi over 2 square units. On the next problem, we want to find the area in one petal of the rows r equals 3 cosine of, let's say, 2 theta. Since coefficient of theta is even, the number of petals will be 4. This rows will look like this. At what angle does it strike the origin? We'll set r equal to 0. You can forget about the 3, that won't matter. Cosine is 0 at pi over 2. If 2 theta is pi over 2, then it is pi over 4, as you can see from the way that we've graphed this. Here's my plan. We'll find the area of half a petal by integrating from 0 to pi over 4, and then we'll just double it. The area will be twice the integral from 0 to pi over 4 of 1/2 r, which is 3 cosine of 2 theta, squared d theta. The 2 will cancel a 1/2. This 3 gets squared and comes out as a 9. We'll have cosine squared of 2 theta. You integrate cosine squared using a half-angle identity. So we'll have 9/2 the integral from 0 to pi over 4 of 1 plus the cosine of 4 pi. What is the period of this function? The period is pi over 2. We're only integrating over half a period, but this is a cosine function, and if you integrate cosine over half a period, you get nothing. This term contributes nothing to the answer. It follows then that the answer is 9/2 times pi over 4, or 9 pi over 8 square units. Find the area of the inner loop of the limmason r equals the square root of 3 minus 2 cosine theta. If you graph this first, you'll find that it looks something like this, and I want the area of the inner loop. So to figure this out, I'm going to need to know these angles at which the curve goes through the origin. So the first step of the solution is to set r equal to 0 and solve for theta. You can see that we have cosine theta is root 3 over 2. It's positive. Cosine is positive in quadrants 1 and 4. So we're looking for the angles in quadrants 1 and 4 where cosine is root 3 over 2. In quadrant 1, that's pi over 6. And in quadrant 4, that's 11 pi over 6. But we need to be careful about this. If we integrate from pi over 6 to 11 pi over 6, we're integrating over the wrong part of the curve. We're integrating to obtain not the area of the inner loop, but the area of the rest of the curve. Instead, we should integrate we should forget about this 11 pi over 6, integrate from 0 to pi over 6, and then double it. The area is going to be the integral, twice the integral from 0 to pi over 6. Alternatively, one could integrate from negative pi over 6 to pi over 6, but it's just simpler to double the integral from 0 to pi over 6. 1/2 r, which was root 3 minus 2 cosine theta squared, all times d theta. These two cancel. We'll be integrating from 0 to pi over 6. Foiling this out, we'll have 3. We'll have this times 2. That's going to be 4 root 3 cosine theta, and then plus the last term squared. That's 4 cosine squared theta d theta. Before applying the fundamental theorem of calculus by finding an antiderivative and evaluating at the endpoints, let's first apply the half angle identity. We'll have 4 times a half times 1 plus cosine 2 theta. Distributing the 2, we'll have 2 and 3 makes 5. We still have minus 4 root 3 cosine theta, and we will also have plus 2 cosine of 2 theta d theta. In this case, we don't get to cross out any terms because we're not integrating over either a full period or a half period for cosine. Integrating, we'll have 5 theta minus 4 root 3 sine theta plus, we'll have to divide by a 2 on this one. That'll leave just sine of 2 theta evaluated from 0 to pi over 6. We'll have then 5 pi over 6. The sine of pi over 6 is 1/2. That'll be minus 2 root 3 plus 2 times pi over 6 is pi over 3. The sine of pi over 3 is the square root of 3 over 2. We should have left this as 4 over 2, because now we can simplify this as 5 pi over 6 minus 3 root 3 over 2. For a slightly more complicated example, suppose I want the area of the region between r equals 2 minus 2 sine theta and r equals minus 6 sine theta. The first curve is a cardioid. When theta is 0, sine is 0, so the radius is 2. Sine of pi over 2 is 1, making the radius 0. Sine of pi is 0, making the radius 2 again. At 3 pi over 2, sine of 3 pi over 2 is negative 1. That would give you a radius of 4. Sine r equals negative 6 sine theta, on the other hand, is a circle. When theta is 0, the radius is 0. When theta is pi over 2, the radius is negative 6. By the time you get to, so the radius goes to negative 6. By the time you get to pi, the radius is back to 0. What I want to do is find the area of the region between these two curves. So the first step is to figure out where it is that these two curves intersect. We can't just set these equal to each other because they intersect when For the second curve, theta is between 0 and pi over 2. The radii are going to be negative there. And for the cardioid, they'll intersect when theta is between pi and 3 pi over 2. The radius here is going to be positive there, and the radius here on the second curve is going to be negative. So to find the points of intersection, we need to do two things. We need to do a phase shift on the first curve compared to the second curve. And on the second curve, we need to change the sign to positive 6 sine theta. This will give us the values of theta where the two curves intersect. Notice that the phase shift of pi to the left for the sine curve gives us a negative sine curve. So we have 2 plus 2 sine theta equals 6 sine theta. Shifting the 2 sine theta over, we have 2 equals 4 sine theta, or sine theta equals 1/2. This gives us, the angles that we get are for the second curve. For the first one, an angle of pi over 6, but with a negative radius. The second curve will go through that point not at pi over 6, but at 7 pi over 6. Here's what we'll do. We'll integrate the first curve from pi over 6 to pi. That'll traverse this segment from here to here, and then double. For the second curve, we'll integrate from 7 pi over 6 to 3 pi over 2, and then double that. The area then is twice the integral from pi over 6 to pi over 2 of our negative 6 sine theta squared d theta. That's the outer curve. And then we have to subtract the inner curve. I forgot my 1/2 here. That's going to cancel. On the second curve, we're going to go from 7 pi over 6 to 3 pi over 2, again yielding only half. That's why we have to multiply by 2. 2 minus 2 sine theta quantity squared d theta. We can see these 2's also cancel. When we square, we're going to have first the integral from pi over 6 to pi over 2 of 36 sine squared. For sine squared, we have to use the half angle identity, 1/2 1 minus cosine 2 theta. The second integral is still from 7 pi over 6 to 3 pi over 2. Foiling it out, we'll have 4 minus 8 sine theta plus 4 sine squared theta, which again is 1/2 1 minus cosine 2 theta. We get a little bit of cancellation here. And so integrating, we have 18 times theta minus 1/2 sine of 2 theta evaluated from pi over 6 to pi over 2 minus, when we distribute the 2, we'll end up with 6. Integrating that, we have 6 theta. When you integrate sine, you get minus cosine, so it's going to be plus 8 cosine theta. We'll have minus 2, we'll have to divide by a 2, so it's minus sine of 2 theta, evaluated from 7 pi over 6 to 3 pi over 2. Evaluating, we have 18 times the sine of 2 times pi over 2. 2 times pi over 2 is pi, sine of pi is 0. We'll subtract what we get when we plug in pi over 6 2 times pi over 6 is pi over 3. Sine of pi over 3 is the square root of 3 over 2. We'll have minus root 3 over 4. That's minus, plugging in 3 pi over 2, we'll have 9 pi, because the 2's cancel. The cosine of 3 pi over 2 is 0. 2 times 3 pi over 2 is 3 pi. Sine of 3 pi is 0. We'll subtract what we get when we plug in 7 pi over 6. The 6's cancel, we have 7 pi. The cosine of 7 pi over 6, it's in the third quadrant, which is a negative quadrant for cosine. That's going to be negative root 3 over 2. 2 times 7 pi over 6 is 7 pi over 3. 7 pi over 3 is in quadrant 1. It's more than all the way around. Although 2 pi is the same as 6 pi over 3. We're at 7 pi over 3 after multiplying by 2, or pi over 3. So that's going to be minus root 3 over 2. Doing the arithmetic step by step, we have 18. Pi over 2 minus pi over 6 is pi over 3. Minus minus is plus root 3 over 4. 9 pi minus 7 pi is 2 pi. We have this minus 8 minus 1 minus 9. Root 3 over 2 minus minus is plus. Distributing the 18, we're going to have 6 pi minus 2 pi. And when 18 multiplies over here, we'll reduce it to, we'll get plus 9 root 3 over 2. That's going to be minus 9 root 3 over 2 for a grand total of 4 pi square units. I have to be honest with you, that last problem is about as nasty as it gets. Let's try to avoid that on the exam. I won't give you something that bad. For our next topic, we're going to talk about arc length. As you saw earlier in the course, arc length was the integral from x naught to x final, square root of 1 plus f prime of x squared dx. But it took a little effort to construct this as our element of arc length. Generally, if our curve is like this, and we take out a little segment here of width ds, dxy, dy high, then ds will be the square root of dx squared plus dy squared. The question naturally arises, what if your curve is given in polar coordinates? X will be r of theta cosine theta, and y will be r of theta sine theta. It follows then that dx d theta is r prime of theta cosine theta minus r of theta sine of theta, and dy d theta is r prime of theta sine theta plus r of theta cosine theta. It follows immediately then that dx is going to be r prime cosine minus r sine times d theta, and dy is r prime sine plus r cosine times d theta. It follows then that the element of arc length, which is the square root of dx squared plus dy squared by the Pythagorean theorem, is r prime cosine minus r sine squared plus r prime sine plus r cosine squared all times d theta. We had a d theta squared on each of these terms, which we factored out of the square root as a d theta. We can't leave it like this. This has to simplify. And so we'll have the square root of r prime squared cosine squared. I'll write this as r prime squared cosine squared minus 2r prime sine cosine plus r squared sine squared, and then plus r prime squared sine squared plus 2r prime sine cosine plus r squared cosine squared. I guess the square root ends here. We do get some cancellation. These two terms cancel each other, and r prime squared cosine squared plus r prime squared sine squared can have the r prime squared factored out, multiplied by cosine squared plus sine squared, which is 1. This simplifies to r prime squared plus r squared all times d theta. And I forgot my d theta over here. This gives us the element of arc length. It follows that if we wish to calculate the arc length, we'll integrate from some theta naught to theta final the square root of r prime squared plus r squared d theta. This is the formula you need to remember. As an example, let's find the arc length of the cardioid 3 minus 3 cosine theta. We'll integrate all the way around, and the formula was the square root of r prime. R prime is going to be 3 sine theta squared plus r squared. Notice we'll have a 3 squared from here. That'll be a 9. We'll also get a 9 out of this. These 9s can come out of the square root as a 3. We're left with 3, integral from 0 to 2 pi, the square root of sine squared plus 1 minus 2 cosine plus cosine squared. Sine squared and cosine squared add up to 1, making a 2 here. So far we have 3, the integral from 0 to 2 pi, the square root of 2 times 1 minus cosine theta d theta. Now, 1 minus cosine theta is almost a half-angle identity. Sine squared theta over 2 is 1/2 1 minus cosine theta. The only thing we're missing is the divided by 2, so I'll put it there because I want it. This 4 is how we pay for it, and it can come out of the square root as a 2, so we end up with 6. The integral from 0 to 2 pi, the square root of sine squared theta over 2. Now, nota bene. The square root of x squared is the absolute value of x. Will that be important here? We'll find out. 0 to 2 pi, the absolute value of the sine of theta over 2. Normally, sine can be positive and negative, but the period here is 2 pi divided by 1/2, or 4 pi. And if you look at the sine curve that's been stretched to have a period of 4 pi, between 0 and 2 pi, it's positive, which means these absolute values are superfluous. Ignoring these absolute values, then, the integral of sine is negative cosine. We have to divide by a half, which is the same as multiplying by 2. 2 times 6 is 12, so I'll have negative 12. And we're evaluating from 0 to 2 pi. Plugging in 2 pi divided by 2 is pi, cosine of pi is negative 1. Cosine of 0 is 1. Our answer is 24. The units of this answer are in linear units because we found the arc length of the cardioid. I want to derive a formula for surface area of surfaces of revolution using polar coordinates. And the idea is something like, suppose we have some curve given as a function of theta, r equals a function of theta, and we revolve this about the x-axis, generating some ham-shaped object. Now, suppose we take a little thin slice. It's going to have a little tiny thickness. It's going to be a little band of length ds. It's going to be swept out. How far? The height, the y value. That radius here of this disk, of this little band, the radius is going to be 2 pi times the y coordinate. So the area of that little strip, if we were to unroll it, snip it and unroll it, would be the length around times this little element of arc length, wide. The length around is 2 pi times y. Y is given by r of theta sine theta. So this is the circumference around. We multiply that by ds to get a little element of surface area. We add up the element of surface area using an integral to find the total surface area. The surface area formula is then the integral from theta naught to theta final of 2 pi r of theta sine theta times the square root of r prime squared plus r squared d theta. For example, suppose I have r equals 1 minus cosine theta, a cardioid. The cardioid looks like this. When theta is 0, we get a radius of 0. At pi over 2, a radius of 1. Radius of 2 at pi, 1 at 3 pi over 2, and then back to 0. If we revolve this about the x-axis, we'll only need to revolve half of the curve from 0 to pi, because that will generate the entire surface. If we integrate from 0 to 2 pi, we'll get double the surface area. So our surface area will be the integral from 0 to pi of 2 pi times my function 1 minus cosine times sine times the square root of r prime, which is sine squared, plus r, 1 minus cosine squared d theta. All we have to do is simplify this. We have integral from 0 to pi 1 minus cosine times sine square root sine squared plus 1 minus 2 cosine plus cosine squared. Sine squared plus cosine squared is 1. We'll make this into a 2 and cancel these off. And we'll factor this 2 out. We'll have 2 root 2 pi integral from 0 to pi. 1 minus cosine sine. We factored the 2 out. we'll have the square root of 1 minus cosine d theta. We have then 2 root 2 pi integral from 0 to pi. Now, 1 minus cosine and the square root of 1 minus cosine can combine. I'm going to write this as sine theta 1 minus cosine theta to the 3 halves d theta. 1 plus a half is 3 halves. At this point, it should be clear that you're dealing with a u substitution. U is 1 minus cosine theta, so that du is sine theta d theta. The integral transforms. First, the limits of integration. If theta is 0, cosine of 0 is 1, 1 minus 1 is 0. The lower limit of integration is still 0. Cosine of pi is negative 1. 1 minus negative 1 is 2. Now the upper limit of integration is 2. Sine theta d theta goes away to become du, and we have u to the 3 halves du. Using the fundamental theorem of calculus, you see that we have u to the 5 halves. We have to multiply by 2/5, evaluated from 0 to 2. Keep in mind that if I raise a number to the power 5 halves, it's like raising it to the 2 plus a half, so I get that number squared times its square root. We have then 2 times 2 is 4, root 2 pi over 5 times 2 root 2 minus 0, or root 2 times root 2 is 2, times 2 is 4, times 4 is 16, pi over 5.